Hello friends, welcome to the video lecture series on digital image processing. I am Dr. Dafda, and in this 69th video class of DIP, we will understand skeletons in image representation for digital image processing and its implementation in MATLAB. We are learning image representation and description, and in image representation, we have already studied chain codes, polygonal approximation, signatures and boundary segments in our previous video classes, and here we will be learning the last technique for image representation, namely skeletons. So starting with the name, what is the meaning of skeleton? Skeleton means medial axis representation of a shape. As the skeleton of human body represents the shape of the human body, similarly skeleton of any shape represents the medial axis of that particular shape. Okay, so let us start. We know that these are the main steps of image processing, and currently we are learning image representation, and after this we will be learning image description. Remember that image representation is used to convert raw output into another format suitable for processing the image, and in image representation, skeletons is the representation of the structural shape of a plane region, reducing it to a graph, and this reduction is obtained by skeleton of a region via thinning algorithm. We have already learned this skeleton in image morphology. However, the procedure that was discussed there made no provisions for keeping the skeletons connected, and the algorithm that we will study here will correct that problem. Okay, so this is the slide that we learned in video lecture number 57, some basic morphological algorithms or applications, where we understood skeletonization and how we obtained this skeletonization. We start by placing a circle inside a shape that touches the boundary at 2 or more points, and we mark the center of the circle as the part of the skeleton, and this is called medial axis point, and we keep moving the circle until we cover the whole shape, and hence we find the skeleton of that particular region. But as mentioned that in this procedure there is no provision for keeping the skeleton connected. Okay, that will be correcting here. We can represent the structural shape of a plane region by reducing it to a graph, and this may be accomplished by obtaining the skeleton of the region via a thinning algorithm. What is skeleton? The skeleton is a thin line that shows the shape and how it is connected. For example, this thin dotted line is the skeleton of this rectangle. So this skeletons has many applications. For example, automated inspection of a printed circuit board, and the definition which we have just understood is based on medial axis transformation or MAT. This MAT is based on prairie fire concept. See, prairie fire means an uncontrolled fire in a grassy area. We can understand this intuitively like this. So this is a grassland having dry grass, and we set up fire along all the borders of this dry grassland at the same time, and the fire will move inwards. So here all fire fronts will advance into the region at the same speed, and the MAT of the region is the set of points reached by one or more fire front at the same time. So at this dash line the fire fronts will meet. So this is the skeleton of this region. Similarly, if the shape is little bit different like this from here, the skeleton will be different like this, and this will be the skeleton of this L-shaped region. So the medial axis transformation generates the skeleton of a region. Now let us understand how to find out MAT of a region R. Say this is a region R, this is border B of region R, and for each point P, say this is a point P in this region R, we find the closest neighbor of B. Okay, so the closest neighbor can be found out using the distance measures that we have studied in video lecture number 5. So here the closest neighbor on border B is this point as well as this point. So it has more than one such point. Okay, so if P has more than one such neighbors, it belongs to medial axis or skeleton of the region. So this P belongs to the skeleton of this region R. Okay, so for each point in the region we find the closest point in the boundary, and if a point has more than one such neighbor, a point belongs to the medial axis or skeleton of the region. And the results of this MAT operation depend on the distance measures, which we have already understood in our video lecture number 5, namely relationship between pixels, neighborhood, adjacency and distance measures. So here we have to find out the closest point in the boundary, and that closest point we find out using either Euclidean distance, the city block distance, or the chessboard distance, using these equations that we have already learned in our video lecture number 5. So this is how we find out different points on the medial axis transformation, or we can say the skeleton using medial axis transformation. But the direct implementation of MAT is computationally expensive, and alternative algorithms have been proposed that thin the boundary of a region until the skeleton is left. And one such alternative algorithm for thinning is like this. There are certain rules for deleting the points. Number 1, that this deletion of points does not remove the endpoints. Number 2, it does not break the connectivity. And number 3, it does not cause excessive erosion of the region. And the algorithm has 2 steps. These steps shows how many neighbors a point has and how many changes there are in the values of its neighbors. So these rules are based on 8 neighborhood notation as shown in this figure. This means that each point P1 has 8 neighbors around it, and we can label them P2, P3 up to P9, and the value of each neighbor can either be 0 or 1 depending on whether it is a part of the shape or the background. If it is background, the value is 0, and if it is a part of the region, the value is 1. In each step, the boundary point that satisfy a set of conditions are flagged and then deleted. In step 1, a point is flagged for deletion if these conditions are satisfied. A, it has at least 2 and at most 6 neighbors with value 1. This means that it is not an isolated or endpoint. B, it has exactly one change from 0 to 1 in the sequence of its neighbors. This means that it is not a corner or a junction point, and at least one of these 3 pairs of neighbors have value 0. That is P2, P4, P4, P6 or P6, P8 have value 0. This means that it is not a part of thin, horizontal, vertical or diagonal line. After step 1 is applied to all the border points, those that are flagged are deleted or changed to 0. In step 2, the conditions A and B remains the same as step 1, but C and D are changed to C dash D dash, that is at least one of these pairs is equal to 0. In step 2, a point is flagged for deletion if all of these conditions are true. This C dash and D dash means that this is not a part of a thin diagonal line in the opposite direction as in step 1. So the points are flagged for deletion in each step are not deleted immediately, but only after all the points have been checked. This prevents changing the shape or connectivity of the region during the process. The 2 steps are repeated until no more points can be deleted, and the result is a thin connected skeleton of the region. Let us check for this P1 whether it will be deleted or not. The number of non-zero neighbors of P1 should be in between 2 to 6. So here the non-zero neighbors are 1, 2, 3 and 4. So 4 is in between 2 to 6. So condition A is satisfied. Condition B says that the number of 0 to 1 transitions should be exactly equal to 1. So here the number of 0 to 1 transition is 1. This is going from 0 to 1. This is from 1 to 0. So it will not be counted. This again is going from 0 to 1. So second transition. This is going from 1 to 0. So not counted. And again it is going from 0 to 1. That is third transition. That means PP1 is equal to 3 and not equal to 1. So this P1 will not be marked for deletion. This means that this point P1 is a point of the skeleton. Got it? Okay. This figure shows human leg bone and skeleton of the bone superimposed on the bone. For most part, the skeleton looks intuitively correct, but there's a double branch on this right side. So at the first glance, we expect that there should be a single branch as the left side, but note here that the right side is somewhat broader than the left side, and that is what has caused the branch to be created by the algorithm. So this type of unpredictable behavior is not unusual in skeletonizing algorithm. So this is how the alternate algorithm works. Let us implement skeleton for this region in MATLAB. You can find the MATLAB code in the description box. That is all for this video class. Thank you very much.